Keep going. All right, so we are continuing our discussion of sets. In this section, we're going to look at a few operations we can do with sets. Okay, and really, that's just ways that we can put sets together. I think I may have mentioned last time we had 3 sections in this chapter. If I did, that's wrong. We have 4. Okay, so we have 2, 3, and 2, 4. 2, 4 is pretty short. Okay, so that won't be too much more than just having this one section today. I don't know, I think that's it. That's all I can think of. So I think we're ready to get right into it. Again, we're still going to look at Venn diagrams in this section. This section, really, we just want to see what these set operations look like on the Venn diagram. The Venn diagrams don't necessarily help us too much solve these problems. Okay, but we will look at those in this section. So to me, when I think about set operations, we've really already talked about one, because I think about taking the complement of a set as a set operation. That's a way to take one set and get a new set out of it. So we've already talked about complement. So we've got 2 more to talk about here. Okay. Our first one is called the intersection of 2 sets. Okay. And the idea here is that if we have 2 sets A and B, then the intersection is going to have all the elements, all the members that are in A and in B. So it's the elements that are in both of our starting sets. Okay. It's the overlap. Okay. So doing this is not hard. And what the trickier part is, we've got 2 set operations we're going to look at. The trickier part's remembering which one's which. Okay. So here with the intersection, something that might help you to remember, if you're driving and you drive through an intersection, what's an intersection of roads? That's where they meet up, right? You got 2 roads that meet each other, and you can almost think about it like one road drives over the other road, right? Because they're both kind of going their own way. So intersection is the overlap. Okay? It's the part that they share in common. That's the intersection. And our notation that goes along with the intersection, this thing right here, it's kind of like an upside down U without a tail. So when I write it, it's just like that. Okay? Or sometimes I do it a little better. Okay? So something like that. Okay? And then this last little bit of notation, it just says the same thing the words say. It says the set A intersect B, or the intersection of set A with the set B, is the set of all elements such that that element is in A and it's in B. So it's in both of the other sets. Thank you. I'll just set it right here for right now. Okay. That is intersection. Okay. So let's make one. Okay. So we've got 2 sets here. And it tells us to make the intersection of the 2 sets. So the way we would write that, we would say we're finding A intersect B, or the intersection of set A with set B. And this thing's still going to be a set, so we'll still have equal and then our curly bracket. And we want all the elements, or in this case, all the letters that are in both of the other sets. So you see any that are in both sets? The first one I see is U. It's in U and, it's in A and in B. R and E. Yeah, R is in both, and E is in both. So that is our intersection. That's like the place where the sets overlap, okay? The elements that are in both sets. Okay. Questions on that one? Got the Got the idea of intersection? All right, so then something else we can look at, again, a Venn diagram doesn't really help us figure this problem out. It's probably easier to do it this way and then draw the Venn diagram, but just to know what the intersection looks like on a Venn diagram, and let's look at it. So we would have a circle for set A, and then a circle for set B, and then those letters that were in both sets would have to be in place where those circles overlap. Okay? And that overlapping part is the intersection. That's the intersection. The place where the circles overlap, that's the intersection. Okay? All right. Okay, so that's the intersection. Let's look at our second operation. Yeah, got a dumb example in here I'm skipping. Go to this one. Okay. Our other set operation is called union. We can find the union of two sets. And what's it mean if you have a union? That means you're putting two things together, or more than two, but you're putting some things together and to make one thing. So you can think about the union of two sets the same way. We're going to take and combine sets to make a union. And our definition says it's the set of all elements that are in A or in B, or in both. It can be in both. And then our notation here, the notation's easier on this one to remember for me because it looks like a U without a tail. So for that, I can remember U as union. And then the way I remember intersection is it's the other one. Okay? Union and intersection. So if an element is in either set, it's going to be in the union. All right, so let's make some unions. Look at this one. This one gives us 3 sets and then gets us to figure out some unions here. So part A, we want the union of set A with set B. So we're looking at these two. So I'm not going to write it down again. We got the name right there up above it. So what elements, what members would be in our set A union B? You can just look and pick them out. If you want to be kind of methodical about it, you want to have a method. One way you can do it is you can look at the first set because you know all the elements in that set have to be in there. So if I look at set A, I know I've got to have 1, 2, 3, 4, and 5 in the union. And then if we look at set B, we just get the ones that we don't have already. You don't, if it's in both sets, you don't have to write it twice. So here 2, we've already got 2 in there, so we don't have to write it again. 4, we've already got in our union, so we don't have to write it again. We're missing 6, so we need 6, and we need 8. Got to make sure they're all covered. So there's our union of set A with set B. Do another one. Let's do A with C. So you can start out the same way if you want to. You can list the ones in the first set. 1, 2, 3, 4, 5. And then when we look at set C, we already have a 1. We already have a 3. We already have a 5. We're missing 7, and then we're missing 9. That's our union. And you probably got it by now, but we might as well do the last one just because it's on here. This time we're doing set B and C. So you could do it the way I've done the other ones. You start out listing like set B, you could do 2, 4, 6, 8. But on this one, you might notice something. It doesn't matter what order you write them in. Okay, but here B's got even numbers and C's got odd numbers. We can make it kind of look nice if we want to. You don't have to, but we can do that. 1, 2, 3, 4, 5, 6, 7, 8. If you do 2, 4, 6 and 1, 3, 5, 7, 9, that's fine. Order does not matter. Question on finding the union? Again, these are not difficult. The part that can trip you up if you're not careful is getting the two mixed up and forgetting which one's which. Remember, union means you're putting them together, and then intersection is where they overlap. Okay, so what about if we had a Venn diagram? What would the union look like on a Venn diagram? Well, we want everything that's in set A, so all that would have to be part of the union. And we also want everything that's in set B, so that's all got to be part of the union. So you end up with this whole Mickey Mouse ear shape thing. Okay? Anything in either one of the circles is part of the union. Sometimes I think people try to think too hard about it, and they try to do everything except where they overlap. You want the overlap too, with the union. Okay. Want all of it. Let's see here. Okay. So if we can do intersection and we can do union, sometimes we have to deal with both in the same problem. So look at a couple of those, get through all these slides here. So this one gives us two sets to find, and we're using intersection and union. If you have multiple set operations going on, you have an order of operations just pretty much just like we have in algebra. So you'll notice this one in intersect K is in parentheses, so we'll do that one first, and that'll give us a new set, and then we'll do M union our new set. We get there. These can look really complicated. They're not, okay, because we're just dealing with two sets at a time. So no matter how long they are, they don't get more difficult. Okay? They get longer, but not harder. Okay, so we'll start by finding N intersect K on this one. So N intersect K. We just want, we're looking at these two. We just want the letters that are in both sets. What do you see that's in both of those? Oh, yeah, I was in both. I see N. Let's see any more. I see one more. What else? E. Yeah, E. I think that's all of them. Okay. O, N, and E are in sets N and NK. So they're in the intersection. And then now we've got our new set. Okay, we found this thing. So now we want to use that new set and do the union with M. So we're using this set and this set, doing a union. So what's that going to get? All right, so if I'm looking at our new set N intersect K, I know I need O, N, and E. And then we can look at M and see if we're missing any. So that one also has an M and an A we don't have yet, and a T and an H. Anyway. Our ultimate goal there is to end up with that set. Questions on doing that one? Anybody confused about what's going on? Okay. All right. We'll see on test day. Okay. So, what's different about B? They look pretty similar, but what's different? The union and the intersection similar in opposite places. They're switched around. Okay, we're still going to start inside the parentheses. Instead of doing N intersect K, we're going to do N union K. So we're looking at these two again. So we need any element that's in either one of those go in the union. So I'm just going to do M-O-N-E-Y from N. And then when I look at K, we don't have I yet. We do already have N. We don't have V yet. We already have an E. We don't have S yet, so we'll put that in there. We don't have T yet. We do have O, but we don't have R yet. There's our union. Okay. Okay, so that's this part. Okay. Now we need to take our new set, do the intersection with M. Okay. Taking this set and this set. Okay. So we're looking for letters that are in both of these sets. So M's in both of these. See any other ones? T, yeah, T's in there. I think that's it. Hey, especially if you have bigger sets, okay, if you're kind of overwhelmed trying to look to see if they're in there, you can be methodical about that too. Like you can start with the first one and say, well, okay, M's in there, so that's, check the next letter. I don't see it. Check T, there it is, so it's going to be in the intersection. And then check H, it's not in there. So you can have a method for checking that too. Those sets are not too big, so they were not that bad. But sometimes it's hard to just look and find it. All right, questions on those? Just start in the parentheses. Just look at two sets at a time, and then they're not bad. Okay. One situation we haven't talked about yet is this. What if we had two sets And we wanted to find their intersection, but they did not have anything in common. And that's a special case. And what we say about those two sets, in that case, when there's nothing in the intersection, and we call those sets, sorry, let me get through this, call those sets disjoint. So if we're trying to find the intersection, trying to find the overlap, and they don't overlap anywhere, let's say the two sets are disjoint. So in that case, we say that the intersection between those two sets is the empty set. So there's the empty set popping back up. And you can think about it the other way around too. You can, if you know the intersection between two sets is the empty set, then that means those two sets are disjoint. So this idea of two sets being disjoint, this kind of sneaks in all over the place, not just in math class. And you'll see that kind of thinking about whether two groups are disjoint or not come up a lot. Disjoint. Okay, so let's see if we can think about whether or not two sets are disjoint. Let's look at this situation. Our universal set here is all students, very general, and just all students. Set A are the students that have a GPA less than 2.5. Set B are students with a GPA greater than 3. And we want to think if those are disjoint, and then we'll draw a Venn diagram. So would those two sets be disjoint? Are there any people in the overlap, in the intersection? No, not on this one, because if you have a GPA less than 2.5, your GPA can't also be greater than 3. Right? You have to be in one or the other. You can't be in both. Okay. So we would say these two sets are disjoint, and then what would our Venn diagram look like in that case? So here's you, and then we got set A. That's a GPA less than 2.5. What's our relationship going to be if they're disjoint, they don't overlap? What are the circles going to look like? They're just completely separate. Good. Just completely separate. I did have one student a few semesters ago that kind of found a loophole in this. The way it's written, it's intended that the sets are supposed to be disjoint. But technically, that student came up with a way that you could possibly have somebody in both. I thought it was pretty smart. So, this is not quite specific enough to ensure 100% that these are disjoint, because the student asked, what if you had somebody that has gone to 2 different schools? Then at one school they could have a GPA less than 2.5, and at another school they could have a GPA greater than 3. That would be in both. So that's pretty sneaky, but thought that was a good point. You would have to make this one airtight. You would have to reword it a little bit. You'd have to say all students at a certain school, or you'd have to say like total GPA or something like that. Just a side note. All right. That's the idea of being disjoint. Okay. This next slide we're going to look at, we've got these laws. Okay? It's just 2 little properties. And they pop up in all kinds of fields. Okay? They're useful in all kinds of different applications. We're actually going to see them twice, okay? Because we'll see them here in chapter 2, and then we'll see them again. I don't remember which chapter. We'll see them again when we do the logic chapter, okay, because they come up again. It looks a little different, but it's the same idea. Okay, so these things are called De Morgan's laws. And they might look kind of complicated, but they're not bad. So the idea here is that if you have a big, complicated string of set operations, we can simplify stuff, kind of like you simplify an equation, get it down to its most simple form. You can do the same thing if you have a bunch of set operations you're doing. And De Morgan's law is really helpful there. It can help us simplify. And also, if you're trying to figure these particular things out by hand, then De Morgan's laws can save you some time too. So what this first one's saying, okay, is saying if we've got A union B, so a union of two sets, and then we want to find, you remember what the tick mark is? It's the complement. That's a complement. So if we want to find the complement of the union of two sets, and then it says the way we can do that is to find the complement of the first set, find the complement of the second set, and then take the intersection. Okay. That might not seem all that useful just looking at it. Okay. But if you're actually doing these things, you would see that it is pretty helpful, because you may not have noticed yet, but when we take a union, we usually end up with a bigger set, right? Because we're putting two sets together. So we have a lot we have to write down. When we find an intersection, we're just doing the overlap, so we usually end up with a smaller set. We don't have to write down as much. Okay, so here this is saying that instead of having to find the union and write down all that and then take the complement of all that mess, okay, we can just find the complement of the two sets and then take their intersection, and that's a smaller set. And then the same thing. And then the bottom one says basically the same thing, except it starts with an intersection and ends with a union. This one, in practice, this one's more useful going this direction. Okay? Instead of having to find this union, we can find this intersection and then take the complement. Okay. So all that's great, but the idea here of writing De Morgan's laws down this way is that you don't have to think about all that conceptually. You don't have to hold all the different ideas of intersections and unions in your head to keep track of what's going on. We can use the symbols, and the symbols kind of do the work for us. We don't have to hold all that information in our brain at once. So it's really easy if you just think about the symbols, what it's telling you. This says if we want to find the complement of this thing, what do we do? It's just kind of like distributive property. We're going to complement the first set, complement the second set, and then what else happens? This thing flips. So it goes from union to intersection. And on the bottom one, the same idea. We complement the first set, complement the second set, and it switches, we just flip the symbol, switches from intersection to union. That's it. Okay. So I haven't made you do like, in the homework I don't either, haven't made you do any like real big sets where you're having to find this kind of stuff. You have to write down a whole lot of stuff. So it's a little bit hard to appreciate how helpful this is. It is helpful, okay? So let's just look at one. I'm not gonna make you write this one down. And you don't have any big long ones in the homework or anything, but just so maybe you can see how it's useful. Let's look at this one. Okay. This one gives us two sets. Gives us the universal set of A through Z, okay, and gives us two sets, and it tells us to verify that this thing equals this thing. So it's, the way we would do that is we would have to show that when we do it this way and when we do it this way, we get the same set. That's what De Morgan's laws tell us. So again, you don't have to write this one down. We'll just look at it. Okay. So doing it the first way, we would have to find the union of A and B. Okay. That's not that bad on this one. Not that big of a set. But then we have to take the complement, and the complement gets long. And the other way, we would take a complement, which on this one's pretty long, B complement, and then find the intersection. And if you check them, you get the same thing both ways. That's all this is showing you. If you're not impressed by that, it's okay. I tried. One more useful thing in this section, okay, called, get through all that, called the inclusion-exclusion principle. And you can actually use this thing in several places throughout this class. So the idea here is we're not necessarily worried about listing out the sets. All we're concerned with this principle, okay, is how many elements each set has. So the inclusion-exclusion principle comes into play when you want to know how many elements, how many members are going to be in a union. Okay? So this is the cardinal number of A union B. That's just how many elements are in there. So if you wanted to find this, you could actually write out the union of the two sets and then count how many elements are in there. That's like the brute force method. But again, remember, you can end up with a really big set when you're finding a union. So instead of doing that, we can use the inclusion-exclusion principle. And what it says is if we want to know how many elements are in a union, we figure out how many are in the first set, how many are in the second set, add those up. But then we might have some elements that are in both of the sets. So we've accidentally double counted those. So we have to subtract away the elements that are in both sets. That way we're not over counting. So it's just how many we have in the first one plus how many we have in the second one minus how many we have in both. And that keeps us from having to actually make this union and skip around it. Okay. So let's use it. Let's use it. Okay. So here we're dealing with a deck of cards. Okay. How many of you actually know all the cards in a deck of cards without having to look at it? One or two. Okay. So that's a problem. We're having to deal with as math teachers. Okay, they're back in the old days. Everybody played cards, so pretty much everybody knew what cards were in a deck of cards. And it's just gotten less popular with the younger generation. So at least this one tells us, okay, what cards are in there. Eventually, as math teachers, we're going to have to find some other example and quit using a deck of cards because nobody knows about a deck of cards. So we're stuck with it for now. Okay, so just in case you're not familiar, okay, standard deck's got 52 cards. Okay, half are red, half are black. Okay, we have 4 suits: clubs, spades, diamonds, and hearts. Clubs and spades are black, diamonds and hearts are red. And since we have 4 suits, 52 divided by 4 means we have 13 of each suit. And it's got the cards listed out. And the way they listed it, they're using an ace as a 1. And then kings, queens, and jacks we call face cards. If you look at a deck of cards, those are the ones that have the people on there. All right, so our task here is to find the number of cards that are either clubs or face cards. So if it's a club, we want to count it. If it's a face card, we want to count it. Okay. Now you could brute force this, okay, and actually list them all out, but I don't want to do that. Okay. So instead, we can use the inclusion-exclusion principle. Okay. So that says we need to figure out, we're looking at clubs, and face cards. Okay, so it means we need to figure out how many clubs we're going to have. It tells us locally we've got 13 of each suit. So that means we have 13 clubs. And then we need to figure out how many face cards we're going to have. It tells us that too. We got 12. That's okay. We've got 12 face cards. But then that number is not going to be quite right. We have to make an adjustment. We have to subtract the cards that are both, right? So we have to subtract the face cards that are clubs. So we'll have a king of clubs, queen of clubs, and a jack of clubs. So we got to subtract 3. Subtract 3. There we get 25 minus 3, so we'd have 22 cards there. If you try to just brute force it and list it out, there's a good possibility you're going to miss one or count one too many times and make a mistake. So it's a really helpful way of coming up with those numbers. And so I probably should label this better. These are clubs. These are face cards. And these are both. Okay. Let's do one more. We'll get there. Oh. Okay. It says find the number of playing cards that are either even or diamonds. So we don't count face cards and things as even. So here it tells us we have 2, 4, 6, 8, 10 that are even cards. So that's 5 of those in each suit, 4 suits. So we have 20 even cards total. And we need to list how many diamonds we have. There's 13 in each suit, so 13 diamonds. And then we have to subtract the even diamonds. So we'll have a 2 of diamonds, 4 of diamonds, 6 of diamonds, 8 of diamonds, 10 of diamonds. So we have to subtract 5. And what do we get there? 33 minus 5 is 28 on that one. Questions on that one? Sure. Subdued today. Very, very quiet. And you look tired. Has it been a long semester already? Starting out that way? Okay. My morning class was that way too. So sometimes the afternoon comes in a little bit more peppy. You've had lunch and maybe some caffeine and stuff like that. Not today though, huh? Not okay. All right. Uh-huh. Yes, that's exactly it. Yeah, because here we're counting them in the evens. So the even diamonds get counted here, and they get counted here. So we don't want to double count, so we have to subtract one counting of them. Yeah, so you're exactly right. Mm-hmm. Yeah. Mm-hmm. Okay, anything else on that before we bail out on it? Okay. That's 2, 3. 2, 4 is pretty short. Let's take a look at it, and then we get a long break from math class. Good whole week. That's I guess. During Thanksgiving break, it'll be 2 weeks between when we meet, so I guess that's the longest time. Okay. All right, so 2.4 sounds really fancy. It says applications and survey analysis. All we're doing is we're doing more Venn diagrams. And then we're using Venn diagrams to help us answer some questions. So really the difference in this section is sometimes we're going to have 3 circles instead of 2. So it just steps up a little bit. You can do a Venn diagram with 4 circles. It gets harder because they all have to overlap somewhere. And really with more than 4, it's too much hassle to usually try to use a Venn diagram. So want to solve problems that involve survey analysis. Okay. And again, we're doing Venn diagrams. Okay. All it is. Okay, so let's look at one. Okay. All right, I've got a Venn diagram, and when you have 3 circles, you usually draw it something like this, because we need them all 3 to overlap, unless we know for sure that a pair is disjoint. Okay. Usually we'll draw them like this, and I don't know, when I draw mine, I usually draw it like with the 2 circles on the top, where it looks more like Mickey Mouse. Okay. But it doesn't really matter. Okay. So let's look at, that's kind of funny, you go to cover your mouth when you cough and you got a mask on. Okay. Look at A. Okay, we've got some new notation here, but we can handle it. This says, what's the cardinal number? How many do we have? And the intersection of set A with B intersected with set C. So all this is saying is how many elements do we have where A, B, and C all overlap? So where does circle A, circle B, and circle C all overlap? That's got to be right in the middle, right, where that all 3 overlap. So how many do we have in there? 1, just 1. So when you see intersection, just anything about Venn diagram, that's just the overlap. B, okay, says how many elements do we have where A and B overlap? Okay, so where do A and B overlap? You have to be a little careful. A and B overlap, let me just, it'd be easier if I draw it here. A and B overlap here. So we've really got 2 little compartments in there. So how do we figure out how many are in there? We just add these 2 pieces together. Right, so we have 6. Our answer would be 6 there. 5 plus 1. Okay. Right. Let's look at the next. Okay. All right, we've got, I'll save this slide flipping. The next thing says go back to this one. So we're here. And it says how many elements do we have in A intersect C? So where A and C overlap, how many do we have there? 9, because that would be A and C overlap there. So we'd have to do 1 plus 8, get 9. Okay. And then the last one says how many do we have where B and C overlap? 11, yeah, because that's this piece. So 1 plus 10 would get 11 in there. Okay. So once you kind of see what's going on, that's not bad. This thing, we're not gonna draw it all out. I'm just gonna show it to you. I don't really like these when you've got all the letters, just because it's a lot to write down. So our universal set's A through Z, and then we've got set A, A-E-I-O-U, B is A through L, okay, and then set C, the letters and alumni, This is draw a Venn diagram to represent the relation between sets. So if you look back at the sets, okay, A and I are in all three sets. Okay, so they're going to be in here. A, E, and I, okay, are in B and in A. A, I, and U are in C and in A. And then A, I, and L are in B and C. And you've got the stuff that's left over that's only in B, the letter that's only in A, and then the ones that are only in C, and then we've got all the junk out here that's left over that's not in any of the other sets. We'll do one kind of similar in a minute. That one's got too much going on, in my opinion. Got too many letters. All right, so the survey analysis part of this, all that is, I mean, it's exactly what it says. It's just where we're analyzing the response to a survey, to a list of questions. And Venn diagrams can be helpful there because if you have different people answered questions the same way, then you can put those in a set, go in a set with each other. All right, so let's look at one. It says a survey of 500 students showed that 350 listened to jazz, 300 listened to classical, and 200 listened to both. Draw a Venn diagram to illustrate this survey. All right, so we need 2 circles on this one because we've got jazz and classical. And we do have some people that listen to both, so how do our circles need to look? They got to overlap. We got to have some in the overlap, right? That listen to both. So here's you. Okay, so call this one jazz. This one classical. Okay. And we want to fill in the rest of the numbers. Okay. When we're doing these, you always want to start where you have the most overlap and work your way out. You'll see why in just a second, because sometimes we're going to have to subtract as we work our way out based on the information they give us. And it really goes back to the exclusion-inclusion principle. We don't want to double count. So the overlap between these two, the place where we have people that listen to both, we have 200 in there. And then what about jazz? So the question now is how many people only listen to jazz? Well, it gives us 350 listen to jazz, but you have to be careful because you're double counting the ones that listen to both if you do that. So what we're doing, why don't we start in the middle? Okay, is we want the whole jazz circle to total up to 350. Well, we've already got 200 in here. So to figure out how many go out here in just the J part, we just subtract. And so we've got 350 in the jazz circle minus 200 is going to leave us 150 up here. Yeah, 150. And that is kind of tricky to think about to start with. Got 150 up there. Okay. And we need to do the same thing for classical. So it says we've got a total of 300 that go in the classical circle, so we want this to total up to 300. So 300 minus 200, we've got 100 out here. 100. Okay. And then we can really go one more step on this one because it tells us the total of how many people were in the survey. It doesn't mention it, but it's possible we had some that said they don't listen to either. So how do we check that? You can figure out, you can either total this up and then subtract, or you can subtract each one. So here we've got, the numbers are pretty easy. So we've got 300 plus 150 is 450. Okay. We had a total of 500 people. So 500 minus 450 means we had 50 people out here that didn't listen to either kind of music. Okay. Subtract there, so we got 50 outside. Makes sense? We need to go back through what we're subtracting. Okay. Yeah. Gotcha. Like if we're like doing the jazz circle. Yeah, we did. So here it says we had 350 that listened to jazz. At the end, yes. Well, the way I did it, so one way you can do it is the way I did it. I added all these up and then subtracted from the total. But you can also take the total. So you could say 500 minus 150 minus 200 minus 100, and you'll get 50 that way too. So whichever way is easier for you to think about. Good question. Thanks for waving at me. Because it's bad. There's mass, so you can't see whose mouth's moving, and then that plexiglass makes it even worse right there. So, like, is it somebody over there? Anything else? Okay. Let's see. Almost there. This section's not too long. All right, let's do a similar one here. We're doing ice cream this time. It says we've got 400 customers. Survey showed 225 customers like chocolate ice cream, 300 customers like vanilla, 200 customers like both. Draw a Venn diagram. So, here's the universe out here. I know we got some that like both, so we got to overlap. And it doesn't matter which one you call vanilla, which one you call chocolate. I'll do them like that. Kind of an ugly circle. Okay. So the key thing on these getting started is really the key thing. We want to start in the middle. We want to start as far inside as we can. So that's where they overlap. So we start with the both customers here. So it says 200 customers like both. I think we had 200 on the last one, didn't we? So it's 200 like both. And then you can do either one of vanilla or chocolate from there. It doesn't matter which order you do it. Let's see. It said 225 like chocolate ice cream. So we want the C circle to total up to 225. We've already got 200 in there. So we'll have 25 out here with chocolate only. And then with vanilla, we had 300 total. We've already got 200 in there. So we'll have 100 vanilla only people. And then outside of both of these, ice cream haters. Okay. So I don't know why they're at ice cream. I guess they're eating some other flavor. They don't like the classics. Okay. So we got total 400. So 400 minus 100 is 300. Minus 200 is 100. Minus 25 leaves us 75 out here. And you can check it. You can, if you add up, okay, you can check each piece, but you can check the whole thing, just add the numbers up and you should get 400. If you want to check the chocolate part, right, it says we had 225 that like chocolate, so just double check 225. You can check yourself that way. Questions on that one? Okay, so now it's time to step it up. Now it's time to go to 3 circles. Go to 3 circles. It's not much worse, but it can be a little more confusing. I'm a little more confused. So, look at this one. It's mostly just because you get so much information thrown at you. All right, so this one says students majoring in international relations are polled on whether they take courses in any of 3 languages, French, German, and Russian. And then it gives us a bunch of information. I'm going to hold off on us even thinking about all that until we get our circle set up. And we know we need 3 circles, French, German, and Russian. So I'm going to go ahead and draw that, and then we can fill it in as we figure stuff out. Okay, so here, if you draw your circles in a different order than mine, you just have to be real careful. Okay, I'm going to do French, German, and Russian. It's just confusing if yours is rotated. You have to be extra careful. Okay. All right, so first thing, before we even read any of the other stuff, where do we want to start? Yeah, we want to start in this very middle. Maybe I should have used 3 different colors. Okay, but we want to start here in this very middle where they all overlap. So we want to look to see if they give us, or if we can figure out how many studied all 3 languages first. Okay. So let's go back. And usually, the way the textbook words them, that's like the last thing they tell you, or one of the last things. So let's see. Does this one even tell us who took all 3? 84 altogether, 55 report taken French, 141. Okay, so we might not get to start right in the middle on this one. Because we don't have, I'm not just overlooking it around, we don't have an all 3 on this one, do we? Okay, all right. So then we've got to find somewhere else to start. Okay. Let's see. So we want as much overlap as we can get. So, oh, I see why. Okay, it says no student who took French also took Russian. Okay, so we can start there, because what that tells us is that in the overlap between French and Russian, we've got zeros. Okay, we've got zeros. So we go back to our overlap between French and Russian. That's these 2. We don't have anybody in there because nobody took both of those. So let me get a different color here. Got a 0 here and a 0 there. That's why I didn't specifically spell out all 3. We had none that took all 3. Okay. Then we kind of want to work our way out. So we'll see if it tells us like the people that took Russian and German, or French and German next. Work our way back. So let's see. If I'm reading down, it says no student who took French also took Russian, and the next one says 39 who took French also took German. So in the overlap between French and German, we've got 39. And since we've got a 0 in all 3, we know they've all got to be in that section. Okay. Got a total up to 39. Then we can look for German and Russian. So let's see. It says 84 who took German also took Russian. Okay, so in the German-Russian overlap, we've got 84. And normally, or don't forget, okay, this one's a little weird, but normally we'd have to take 84 and subtract the 1 in all 3, but we didn't have any in all 3 on this one. Okay. And once we get those pieces finished, we want to look for just totals. We want to say like a total of how many took French, a total of how many took German, or a total of how many took Russian. Those are the easiest ones to do there. So, all right, if we're just going in order of how we read, it says altogether 55 reported taking French. So we know the F circle has to total up to 55. We've got 39 in there already. So we do 55 minus 39. We get 16. Okay. German, let's see, it says 141 reported taking German. So our German total got to be 141. We already have 39 in there, so we got to subtract 39, and then we got to subtract 84 that's in there as well. End up with 18. And then the last one says 92 reported taking Russian. Okay, so the R circle's got a total of 92. So 92 minus 84. That's 8. And then we've got the most annoying part. Do we? We might get away with it on this one. Okay, all right. This one doesn't make us do it, but sometimes you have one more step, because if it tells you the total number of people in the survey, what do you have to do? You have to take the total. This one doesn't tell us, so luckily we get to skip it. You have to take the total and then subtract all of these to figure out how many would be out here in you. Okay. This one I got to be a little lazy on. We didn't have to do that part. Okay. And then we need to walk through it. I had a lot going on. We need to walk through part of it again. Okay. Some of you are like, no, we really don't need to go through it again. Okay. One more, we'll be done. Okay. Same idea, just a different survey. Is we got a survey of shoppers, found that 225 shoppers like bananas, 198 like apples, 180 like grapes, 25 shoppers like all. Okay, we get all that. So we know what 3 circles we need to make. And we need one for bananas, one for apples, one for grapes. I'm gonna do bananas, apples, and grapes. We want to start at the inside, okay, where all 3 overlap if we can. Nope. On this one, it's nice to us. It just tells us, it says 25 like all 3. So 25 goes right in the middle. And then we can work our way out from there. Now we're looking for the overlap between 2 fruits. Let's see what we see. First one my eye caught is there are 110 shoppers that like bananas and apples. So the overlap between bananas and apples would need to be 110. This part. We already have 25 in there. So 110 minus 25 is 85. And it says 58 like apples and grapes. So we need apples and grapes to total 58, so we already have 25. 58 minus 25. 33. And then bananas and grapes, what we're missing here. So last line says 55 like bananas and grapes. So 55 minus 25, 30. Then we can work our way out to like the total bananas, total apples, total grapes. So let's see if we go back to the beginning here. There's 225 like bananas. So we have to do 225 minus, we've got 3 pieces in there, right? We got to do minus 30, minus 25, and minus 85. That leaves us 85. Apples, what we got? 198 for apples. So do 198 minus, we got 3 numbers, 85, 25, and 33. 55. And grapes is 180 like grapes. So 180 minus 30 minus 25 minus 33, yeah, 92. And so you have a couple problems that give you the Venn diagram and get you to fill the numbers in, and then you'll have a problem or two that give you that information they gave you, and then it'll say like how many people only like apples, and you have to do at least part of the Venn diagram to figure out. You'd have 55 that only like apples on that one. So you all right? Like you're ready for a week off from math or something? Like you're ready to get out of here or something? All right, if you didn't sign the signing sheet, it's up here on the front table. Get it on your way out. I will see you next week.